Glasses of champagne out on the dance floor. Hanging with some girls I never seen before. You used to call.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Let's talk about the charge distribution in molecules. So electron distribution influences the shape of proteins, enzymes, RNA, DNA, etc. And biomolecules lose their shape and they do not function. And so this is a really critical aspect of chemistry. And so first, let's talk about polar bonds. So let me write that right here. So this is when you have a heteronuclear covalent bond. Heteronuclear covalent bond. And what that means is that electrons are not equally shared. If you had a homonuclear covalent bond, that means the electrons are equally shared. And so an increasing difference in electronegativity, which I'll write down as delta En, leads to an increasing difference in charge, which finally leads to an increasing ionic character of the covalent bond. And so this flow results in more polar bonds. And so the charge difference can be measured and is called an electric dipole moment. And it's given the letter mu right here. And this is in units called devi, which is given this term D. And this is in coulombs and meters, where coulombs is a unit for charge and meters is a unit for distance. So if you look at this equation right here, the dipole moment is equal to the separated charge multiplied by the distance between them. And so if you have a positive charge and a negative charge, the charge is calculated in coulombs and the distance between the center of the two charges is given R in terms of meters. And so from here, the dipole is represented by an arrow pointing towards the slightly more negative atom. And so let's look at HF. If you remember the periodic table trends, which we talked about before, remember that electronegativity increases diagonally up towards the top right corner, where you have elements like fluorine. And so since hydrogen is way over here, fluorine is much more electronegative than hydrogen. So there's a big difference in electronegativity, so there's an increasing difference in charge, and thus there's an increasing ionic character of the covalent bond. And what that means is the electron cloud is pulled more towards the fluorine. So let me draw this for you in a bond form too, where fluorine pulls electrons more towards itself, because electronegativity means that it wants to pull those electrons towards itself. And so the fluorine ends up gaining a slightly negative charge, as shown right here, and the hydrogen gains a slightly positive charge, as shown right here. And as I mentioned before, the dipole is represented by an arrow pointing towards the slightly negative atom. And so another example is this water molecule. You have H2O, and in this case, oxygen is more electronegative than the hydrogen atom. And so we have delta minus, delta plus, delta plus. And so the direction goes towards the negative atom, and the overall molecular dipole moment goes up in this case. And so this is considered a polar molecule because it has a molecular dipole moment. On the other hand, let's look at methane. We have, actually, I'm sorry, this is not methane because we have this fluorine atom right here. If this was a hydrogen, it would be CH4, but in this case, we have CH3 and then a fluorine. So fluorine is one of the most electronegative atoms, and so the dipole moment would be going towards the slightly negative fluorine. In this case, carbon is more electronegative than hydrogen, and so comparing these two, we're going to have a slightly negative charge of the carbon and a slightly positive charge of the hydrogen. However, the difference in the electronegativities, as shown right here, is greater between the carbon and the fluorine, and so this is going to dominate. And this is also a polar molecule because it has a molecular dipole moment headed towards the fluorine. Finally, for carbon dioxide, oxygen is the more electronegative atom, and so we have a slightly negative charge here. Carbon is slightly positive, and oxygen is slightly negative. This is actually a non-polar molecule. The reason for that being that these two arrows going in opposite directions cancel out these polar movements. And so this is going to be a non-polar molecule, whereas this guy with the molecular dipole moment is going to be polar. So a covalent bond with a dipole moment is called a polar covalent bond. And just as a fun fact, which might be useful to know, a single negative charge, so an electron, and a single positive charge, let's say just a positive charge right here, separated by 1 angstrom as the distance, so it's this R value right here, has a dipole moment of 4.80 devi.
Late night when you need my love. Call me on my cell phone.